What if the key to unlocking the secrets of the universe lies not in the stars above, but in the very fabric of time itself? For centuries, humanity has been captivated by the idea of time travel, a concept that blurs the line between science and imagination. From ancient myths to modern blockbusters, the notion of bending time has sparked endless curiosity and debate. But what if time travel isn't just the stuff of fiction? What if it's a real possibility, waiting to be unraveled by the brightest minds in science? Today, we're diving into 20 groundbreaking theories that could explain how time travel might actually work. From Einstein's mind-bending equations to the mysterious realms of quantum mechanics, each theory offers a unique glimpse into the tantalizing possibilities of traversing time. So, buckle up and prepare to explore the unknown, because by the end of this journey, you might just find yourself questioning everything you thought you knew about time, space, and reality itself. Let's begin. Now, let's step into the realm of one of the most revolutionary ideas in science, Einstein's theory of relativity. This theory didn't just change how we understand gravity, it completely reshaped our perception of time itself. At its core, Einstein proposed that time and space are not separate entities but are interwoven into a single fabric called spacetime. This means that time isn't a fixed, unchanging force, it's flexible, bending and stretching under the influence of gravity and motion. One of the most fascinating consequences of this idea is time dilation. Imagine two identical twins. One stays on Earth while the other embarks on a journey through space at speeds close to the speed of light. When the traveling twin returns, they'll find that less time has passed for them compared to their sibling on Earth. This isn't science fiction, it's a real phenomenon predicted by Einstein's equations. The faster you move, the slower time ticks for you relative to someone moving at a slower speed. This leads us to the twin paradox, a thought experiment that highlights how time travel to the future could theoretically be possible. If you could build a spacecraft capable of reaching near light speeds, you could effectively leap forward in time. While only a few years might pass for you, decades or even centuries could go by on Earth. It's a mind-bending concept, but it's grounded in the very real science of relativity. Einstein's work shows us that time isn't as rigid as we once thought. It's a dynamic, malleable dimension that can be influenced by speed and gravity. And while we're still far from building a time machine, his theories give us a tantalizing glimpse into how the universe might allow for the possibility of time travel. So, as we move forward, keep this idea in mind: time is not just a clock ticking away. It's a dimension we might one day learn to navigate. Next, we'll explore another fascinating concept that could unlock the secrets of time travel: wormholes. These cosmic shortcuts might just be the key to bending spacetime in ways that could take us to the past or the future. Let's dive in. Now, let's venture into the intriguing world of wormholes, a concept that sounds like it's straight out of science fiction but is deeply rooted in the science of spacetime. Imagine a tunnel that cuts through the fabric of the universe, connecting two distant points in space and time. That's essentially what a wormhole is: a theoretical passage that could allow us to travel vast distances or even backward and forward in time without covering the immense space in between. Wormholes emerge from Einstein's equations of general relativity, which describe how massive objects warp spacetime. Under the right conditions, this warping could create a bridge between 2 points, forming a shortcut. Think of it like folding a piece of paper so that 2 distant dots touch instead of traveling along the surface. You could punch through the fold. This idea has captured the imagination of scientists and storytellers alike, offering a potential way to bypass the limitations of light-speed travel. But here's the catch: wormholes, as fascinating as they are, come with some serious challenges. For one, they're incredibly unstable. Even if a wormhole were to form naturally, it would likely collapse almost instantly under its own gravitational forces. To keep a wormhole open, scientists propose the need for something called exotic matter, a hypothetical substance with negative energy or mass. This exotic matter could counteract the wormhole's tendency to collapse, acting like a kind of cosmic glue to hold it open. The problem: exotic matter has never been observed in nature, and its existence remains purely theoretical. Even if we could find or create it, the amount required to stabilize a wormhole would be staggering. And let's not forget the other hurdles, like navigating the intense gravitational forces inside a wormhole or ensuring it doesn't lead to a dead end, or worse, a black hole. Despite these challenges, the idea of wormholes continues to inspire both scientists and dreamers. They represent a tantalizing possibility, a way to bend the rules of space-time and explore the universe in ways we can barely imagine. So, while we're still far from building a wormhole time machine, the concept reminds us that the universe is full of mysteries waiting to be unraveled. Next, we'll take a closer look at another mind-bending idea: closed time-like curves. These are solutions to Einstein's equations that could create loops in time, potentially allowing for time travel without the need for wormholes. Stay tuned as we dive deeper into this fascinating concept. Now, let's shift our focus to another fascinating concept that could unlock the secrets of time travel: closed time-like curves. These are not just abstract ideas, they're solutions to Einstein's equations of general relativity that suggest the possibility of loops in time. Imagine a path through space-time that circles back on itself, allowing you to return to the same point in time and space. This is the essence of a closed time-like curve, a theoretical loop that could, in principle, enable time travel. To understand how this works, let's revisit Einstein's theory of spacetime. According to general relativity, massive objects like stars and planets warp the fabric of spacetime, creating what we perceive as gravity. In extreme conditions, such as near a rotating black hole or in the presence of incredibly dense matter, this warping could become so intense that spacetime twists into a loop. If you were to follow this loop, you could theoretically travel back to an earlier moment in time without ever leaving your own timeline. But here's where things get tricky. Closed time-like curves raise some serious questions about causality, the relationship between cause and effect. For example, what happens if you travel back in time and prevent your own birth? This is a variation of the grandfather paradox, where your actions in the past could create a logical contradiction. If you were never born, how could you have traveled back in time in the first place? These paradoxes challenge our understanding of how time works and whether the universe has built-in mechanisms to prevent such contradictions. Some scientists propose that the universe might resolve these paradoxes through what's known as the Novikov self-consistency principle. This idea suggests that any actions taken by a time traveler were always part of history, meaning you couldn't change the past in a way that creates a contradiction. In other words, if you tried to prevent your own birth, the universe would somehow ensure that your attempt fails, preserving the timeline as it always was. While this might sound like a convenient way out, it raises questions about free will and whether our actions are truly our own. Despite the paradoxes, closed time-like curves remain a compelling area of study for physicists. They offer a way to explore the boundaries of our understanding of time and space, pushing us to rethink the fundamental laws of the universe. While we're still far from proving their existence or harnessing them for time travel, the concept reminds us that the universe is far stranger and more complex than we often imagine. Next, we'll explore another intriguing idea: the Tipler cylinder. This hypothetical object, named after physicist Frank Tipler, could create a space-time loop through sheer rotational force. Stay tuned as we dive into how this massive, spinning cylinder might hold the key to bending time itself. Now, let's turn our attention to another mind-bending concept in the realm of time travel: the Tipler cylinder. Named after physicist Frank Tipler, this theoretical object is a massive, infinitely long cylinder spinning at near light speeds. The idea is that such a cylinder could warp spacetime so dramatically that it creates a loop, allowing for the possibility of time travel. But how exactly does this work, and what would it take to build one? To understand the Tipler cylinder, we need to revisit the idea of spacetime curvature. According to Einstein's general relativity, massive objects can bend the fabric of spacetime. The Tipler cylinder takes this to the extreme. As it spins at incredible speeds, it drags spacetime along with it, twisting it into a loop. If you were to travel around this cylinder in the right direction, you could theoretically follow this loop and end up at an earlier point in time. It's like running on a cosmic treadmill that bends time itself. But before we get too excited, let's talk about the practical challenges. First, the Tipler cylinder would need to be infinitely long to create a stable spacetime loop. In reality, constructing something of infinite length is, well, impossible with our current understanding of physics and engineering. Even if we could build a finite version, it would still require an unimaginable amount of energy to spin it at near light speeds. We're talking about energy levels far beyond anything humanity has ever produced or even conceived of. Another major hurdle is the material required to build such a cylinder. It would need to be incredibly dense and strong enough to withstand the immense forces generated by its rotation. Current materials science simply doesn't offer anything close to what would be needed. And let's not forget the potential dangers. A spinning cylinder of that magnitude could have catastrophic effects on its surroundings, tearing apart anything that gets too close. Despite these challenges, the Tipler cylinder remains a fascinating thought experiment. It pushes the boundaries of our understanding of physics and forces us to think creatively about the nature of spacetime. While it's unlikely we'll see a Tipler cylinder built anytime soon, the concept reminds us that the universe is full of possibilities we've yet to explore. Next, we'll delve into another intriguing theory: cosmic strings. These one-dimensional defects in spacetime could hold the key to warping reality itself. Stay tuned as we uncover how these cosmic threads might weave the fabric of time. Now, shifting our focus to another fascinating concept, let's explore cosmic strings. These are theoretical one-dimensional defects in spacetime, remnants from the early universe that could hold the key to bending the very fabric of reality. Imagine them as ultra-thin, incredibly dense threads stretching across the cosmos, carrying immense gravitational energy. But how could something so small and seemingly insignificant play a role in time travel? Cosmic strings are thought to have formed during the rapid expansion of the universe just after the Big Bang. As the universe cooled, these strings could have been left behind like cracks in ice as it freezes. What makes them so intriguing is their ability to warp spacetime around them. If a cosmic string were to pass by, it could create a gravitational field so intense that it distorts time itself. This distortion could, in theory, create closed time-like curves, loops in time that allow for travel to the past. But here's where it gets even more interesting. If two cosmic strings were to move past each other at incredibly high speeds, they could create a spacetime loop. This loop could act as a sort of time machine, allowing an object or even a person to travel back in time. It's like threading a needle through the fabric of time, creating a path that defies our everyday understanding of cause and effect. Of course, the challenges are immense. First, cosmic strings are purely theoretical at this point. While they fit neatly into certain models of the universe, we have no direct evidence of their existence. Detecting something so thin and dense would require technology far beyond what we currently possess. Even if we could find one, harnessing its power would be another matter entirely. The energy required to manipulate a cosmic string would be astronomical, and the risks of destabilizing spacetime are significant. Despite these hurdles, cosmic strings remain a captivating idea. They remind us that the universe is full of mysteries waiting to be unraveled. While we may not be building a time machine from cosmic strings anytime soon, the concept pushes us to think bigger and explore the boundaries of what's possible. Next, we'll dive into the strange and fascinating world of quantum mechanics, where particles can exist in multiple states at once, and the rules of time might not be as rigid as we think. Stay with us as we uncover how the quantum realm could hold the secrets to time travel. Now, let's step into the strange and mind-bending world of quantum mechanics, where the rules of reality seem to bend and twist in ways that challenge our understanding of time itself. Quantum mechanics, the branch of physics that deals with the behavior of particles at the smallest scales, opens up a realm of possibilities that could redefine how we think about time travel. One of the most intriguing aspects of quantum mechanics is quantum tunneling. This phenomenon allows particles to pass through barriers that, according to classical physics, should be impossible to overcome. Imagine a ball rolling up a hill and, instead of stopping at the top, suddenly appearing on the other side without ever climbing over it. In the quantum world, particles can do just that, appear on the other side of an energy barrier without actually crossing it. This strange behavior hints at the idea that particles might be able to tunnel through time as well, bypassing the usual flow of cause and effect. Then there's superposition, a cornerstone of quantum mechanics. Superposition allows particles to exist in multiple states at once until they are observed or measured. Think of it like a coin spinning in the air. It's neither heads nor tails until it lands. In the quantum realm, particles can be in multiple places or states simultaneously, suggesting that time itself might not be as linear as we think. If particles can exist in multiple states at once, could time also exist in multiple states, allowing for the possibility of traveling between them? Quantum entanglement adds another layer of mystery. When two particles become entangled, their properties are linked no matter how far apart they are. Change one and the other instantly changes, even if they're light years apart. This instantaneous connection seems to defy the speed of light and, by extension, our understanding of time. Some scientists speculate that entanglement could be a gateway to manipulating time, creating connections that transcend the usual flow of past, present, and future. But how does all this translate to time travel? If particles can tunnel through barriers, exist in multiple states, and instantaneously influence each other across vast distances, it's possible that these quantum phenomena could be harnessed to create pathways through time. Imagine a device that uses quantum tunneling to bypass the usual constraints of time, or exploits entanglement to create a bridge between different moments in history. Of course, the challenges are immense. Quantum mechanics operates on scales so small that translating these phenomena into something practical for time travel would require technology far beyond our current capabilities. And even if we could harness these effects, the implications for causality and the nature of reality would be profound. Would time travel at the quantum level create new timelines, or would it simply reveal the interconnectedness of all moments in time? As we continue to explore the quantum realm, one thing is clear: the rules of time as we know them may not apply. Quantum mechanics invites us to rethink the very fabric of reality, offering tantalizing hints that time travel might not be as far-fetched as it seems. Next, we'll venture into the multiverse, where parallel universes and alternate timelines could hold the key to resolving some of the most perplexing paradoxes of time travel. Stay with us as we unravel the mysteries of the multiverse and its implications for our understanding of time. Now, let's take a leap into the vast and mind-expanding concept of parallel universes and the multiverse. Imagine a reality where every decision you've ever made or could have made spawns an entirely new universe. This is the essence of the multiverse theory, a fascinating idea that suggests our universe is just one of countless others, each with its own unique timeline and set of events. But what does this have to do with time travel? Well, the multiverse might just hold the key to solving some of the most perplexing paradoxes that time travel presents. One of the biggest challenges in time travel is the grandfather paradox. Imagine traveling back in time and accidentally preventing your own existence. If you were never born, how could you have traveled back in time in the first place? It's a logical loop that seems impossible to resolve, but the multiverse theory offers a way out. According to this idea, every possible outcome of an event creates a new universe. So, if you traveled back in time and changed something, you wouldn't be altering your own timeline. You'd simply be branching off into a new one. In this new universe, your actions might prevent your existence, but the original timeline where you came from would remain untouched. This means you could, in theory, change the past without erasing yourself from existence. The multiverse theory also suggests that time travel might not involve moving through time within a single universe, but rather hopping between parallel realities. Each universe could represent a different moment in time, allowing you to effectively travel by shifting from one reality to another. This idea not only sidesteps the grandfather paradox, but also opens up endless possibilities. Want to see what the world would look like if a major historical event had gone differently? Just find the universe where that alternate outcome exists. But how does this work in practice? Some theories propose that quantum mechanics could play a role. For instance, quantum superposition, where particles exist in multiple states at once, might extend to entire universes. In this view, every possible universe exists simultaneously, and time travel could involve navigating between them. Others suggest that black holes or wormholes might serve as gateways between these parallel realities, offering a physical pathway for such journeys. Of course, the multiverse theory is still speculative, and the idea of traveling between universes raises its own set of questions. How would we locate a specific universe? What would it take to move between them? And what happens to the version of you in the new universe? These are questions that scientists and theorists are still grappling with, but the multiverse offers a compelling framework for thinking about time travel in a way that avoids the pitfalls of paradoxes. As we ponder the possibilities of parallel universes, it's clear that the multiverse theory doesn't just expand our understanding of time, it redefines it. By introducing the idea of infinite realities, it challenges us to think beyond the constraints of a single timeline and imagine a cosmos where every possibility exists. Next, we'll explore how time itself might be more than just a straight line as we dive into the concept of time as the fourth dimension. Stay tuned as we continue to unravel the mysteries of time travel. Now, let's shift our perspective and consider time not just as a sequence of events, but as a dimension in its own right. Just as we move freely through the three spatial dimensions, length, width, and height, time is often described as the fourth dimension. But what does it mean to think of time this way, and how could it open the door to time travel? To understand this, imagine a simple analogy. Picture a line drawn on a piece of paper. That line exists in one dimension, length. Now add a second dimension by drawing a square. Suddenly you have width as well. Add a third dimension and you've got a cube with depth. Time as the fourth dimension is like adding another layer to this structure. It's the dimension that allows us to move from one moment to the next, creating the flow of events we experience as life. But here's where it gets fascinating. If time is a dimension, could we learn to move through it as freely as we move through space? The idea isn't as far-fetched as it might seem. In fact, Einstein's theory of relativity already treats time as a dimension intertwined with space, forming what we call spacetime. This means that just as you can move forward, backward, left, or right in space, it might be possible to move forward or backward in time under the right conditions. One way to visualize this is to think of spacetime as a fabric. Massive objects like stars or planets create curves or dips in this fabric due to their gravity. These curves can influence not just the path of objects moving through space, but also the flow of time itself. For example, time moves slower near a massive object like a black hole compared to a region with less gravity. This phenomenon, known as time dilation, suggests that manipulating spacetime could, in theory, allow us to travel through time. But what about higher dimensions? Some theories propose that our universe might have more than just 4 dimensions. String theory, for instance, suggests there could be up to 10 or 11 dimensions, most of which are curled up and hidden from our perception. If these extra dimensions exist, they could hold the key to time travel. For example, a 5th dimension might allow for shortcuts through space-time, enabling us to bypass the limitations of moving through time in a linear fashion. Imagine a scenario where you could step into a higher dimension, move along it, and then step back into our 4-dimensional world at a different point in time. This would be like taking a detour on a road trip. Instead of following the long, winding path, you find a shortcut that gets you to your destination faster. While this remains speculative, it's an exciting possibility that challenges our understanding of reality. Of course, the idea of moving through time as a dimension raises its own set of questions. How would we access these higher dimensions? What kind of technology or energy would be required? And what would it feel like to experience time as a dimension we can navigate? These are questions that scientists and theorists are still exploring, but the concept of time as a dimension opens up a whole new way of thinking about time travel. As we wrap up this exploration, it's clear that viewing time as a dimension doesn't just change how we think about time travel, it changes how we think about time itself. It challenges us to see the universe not as a static collection of moments, but as a dynamic, multidimensional tapestry where past, present, and future might all coexist. Next, we'll dive into the mysterious world of black holes and how their immense gravitational pull could warp time itself. Stay tuned as we continue to unravel the secrets of time travel. Now, let's turn our attention to one of the most mysterious and awe-inspiring phenomena in the universe: black holes. These cosmic giants, with their unimaginably strong gravitational fields, don't just bend space, they warp time itself. But how exactly do black holes play into the possibility of time travel, and what challenges would we face if we ever tried to approach one? To understand this, let's start with the basics. A black hole is formed when a massive star collapses under its own gravity, creating a region of space where gravity is so intense that nothing, not even light, can escape. This boundary, known as the event horizon, marks the point of no return. Once something crosses it, there's no coming back. But what happens to time near a black hole? According to Einstein's theory of relativity, time slows down in the presence of strong gravitational fields. Near a black hole, this effect becomes extreme. For someone observing from a safe distance, time would appear to almost stand still for an object falling toward the event horizon. This phenomenon, known as gravitational time dilation, suggests that if you could somehow orbit a black hole without falling in, time would pass much more slowly for you compared to someone far away. In theory, this could allow you to travel into the future. Imagine spending a few hours near a black hole and returning to find that decades or even centuries have passed on Earth. It's a mind-bending concept, but it's grounded in the laws of physics. However, the idea of using black holes for time travel comes with significant challenges. First, there's the issue of survival. The intense gravitational forces near a black hole would stretch and compress anything that gets too close, a process known as spaghettification. Even if you could avoid being torn apart, the radiation and extreme conditions near a black hole would make it nearly impossible to survive. And then there's the event horizon itself. Once you cross it, there's no turning back. You'd be pulled inexorably toward the singularity at the center, where the laws of physics as we know them break down. But what if black holes could be used in a different way? Some theories suggest that black holes might be connected to other regions of spacetime through wormholes, hypothetical tunnels that could allow for shortcuts across the universe or even through time. While this remains speculative, it's an intriguing possibility that ties black holes to the broader concept of time travel. As we explore these ideas, it's important to remember that black holes are still one of the least understood objects in the universe. Their extreme nature makes them both fascinating and dangerous, and while they offer tantalizing possibilities for time travel, they also present immense challenges. Next, we'll delve into the concept of time crystals, a new phase of matter that could revolutionize our understanding of time itself. Stay with us as we continue to uncover the secrets of time travel. Now, let's shift our focus to a groundbreaking discovery that could redefine our understanding of time itself: time crystals. Unlike ordinary crystals, which have repeating patterns in space, time crystals exhibit a unique property: they repeat their structure in time. This means they oscillate between states without any external energy input, creating a form of perpetual motion at the quantum level. First proposed by Nobel laureate Frank Wilczek in 2012, time crystals challenge our traditional notions of matter and open up fascinating possibilities for time travel. So, how do time crystals work? Imagine a clock that ticks endlessly without needing to be wound. Time crystals operate in a similar way, but on a much smaller scale. Their atomic structure cycles through a series of states in a predictable, repeating pattern, even in their lowest energy state. This behavior defies the usual rules of thermodynamics, which state that systems tend to settle into equilibrium. Time crystals, however, never reach equilibrium. They keep moving, creating a stable, repeating loop in time. This unique property has led scientists to speculate about their potential applications in time travel. If we could harness the repeating patterns of time crystals, it might be possible to create stable time loops, structures where events repeat in a controlled manner. Such loops could serve as a foundation for building devices that manipulate time, allowing us to revisit moments or even send information backward or forward in time. While this is still theoretical, the implications are staggering. Time crystals could offer a way to explore time travel without the extreme conditions required by black holes or wormholes. However, there are significant challenges to overcome. Time crystals exist only under very specific conditions, often requiring ultra-cold temperatures and precise control. Scaling them up for practical use is still a distant goal, and their behavior at larger scales remains poorly understood. Despite these hurdles, the study of time crystals is advancing rapidly, with experiments already demonstrating their existence in controlled environments. As we continue to unravel the mysteries of time crystals, one thing is clear: they represent a bold new frontier in physics. By exploring their potential, we may unlock new ways to understand and manipulate time itself. Next, we'll dive into the Novikov self-consistency principle, a fascinating idea that suggests the universe might prevent paradoxes by ensuring that any actions taken by a time traveler were always part of history. Stay tuned as we explore how this principle could shape the future of time travel. Now, let's turn our attention to a principle that offers a fascinating solution to one of the biggest challenges of time travel: the Novikov self-consistency principle. Proposed by Russian physicist Igor Novikov in the 1980s, this idea suggests that the universe has a built-in mechanism to prevent paradoxes. According to this principle, any actions taken by a time traveler were always part of history, meaning they cannot change the past in a way that creates contradictions. In other words, if you traveled back in time, your actions would already be woven into the fabric of events, ensuring that history remains consistent. To put it simply, imagine trying to go back in time to prevent a historical event. The Novikov self-consistency principle argues that no matter what you do, your actions would somehow align with what already happened. For example, if you try to stop a famous battle, your efforts might inadvertently cause it to happen exactly as it did. This principle suggests that the universe is self-correcting, ensuring that time travel doesn't disrupt the timeline. But what does this mean for free will? If our actions in the past are predetermined to fit into the existing timeline, does that mean we don't truly have control over our choices? This is where the Novikov principle becomes particularly intriguing. It implies that while we may feel like we're making independent decisions, those decisions are already part of a larger, unchangeable sequence of events. This raises profound questions about the nature of free will and whether our sense of autonomy is an illusion. Despite its philosophical implications, the Novikov self-consistency principle offers a practical advantage. It eliminates the risk of paradoxes like the grandfather paradox, where a time traveler could prevent their own existence. By ensuring that all actions are consistent with history, the principle provides a framework for time travel that avoids logical contradictions. However, it also challenges our understanding of causality and the flow of time, suggesting that the past, present, and future might be more interconnected than we realize. As we continue to explore the possibilities of time travel, the Novikov self-consistency principle reminds us that the universe might have its own rules to maintain order. Next, we'll delve into the many worlds interpretation, a theory that takes a completely different approach to resolving time travel paradoxes by suggesting that every possible outcome creates a new reality. Stay tuned as we uncover how this idea could reshape our understanding of time and existence. Now, let's shift our focus to a theory that takes a radically different approach to time travel, the many worlds interpretation. Unlike the Novikov self-consistency principle, which keeps the timeline intact, this theory suggests that every decision or event creates a new, parallel universe. Imagine stepping into a time machine and traveling to the past. According to the many worlds interpretation, your actions wouldn't alter the original timeline. Instead, they would create an entirely new branch of reality where the consequences of your choices unfold independently. This idea stems from quantum mechanics, where particles can exist in multiple states simultaneously until observed. The many worlds interpretation extends this concept to the macroscopic world, proposing that every possible outcome of an event actually happens, but in separate, parallel universes. For example, if you traveled back in time and prevented a historical event, you wouldn't be changing the past in your original universe. Instead, you'd be creating a new timeline where that event never occurred, while the original timeline remains untouched. One of the most compelling aspects of this theory is how it resolves time travel paradoxes. Take the grandfather paradox, where a time traveler prevents their own existence. In the many worlds interpretation, this paradox simply doesn't exist. If you went back in time and altered events, you'd be branching off into a new reality where your actions have no effect on the original timeline. This means you could theoretically change the past without creating logical contradictions, because the original sequence of events remains preserved in its own universe. However, this theory also introduces its own set of challenges. If every possible outcome creates a new reality, the number of parallel universes becomes infinite. This raises questions about the nature of identity and existence. Are there infinite versions of you, each living out different choices and outcomes? And if so, does that diminish the significance of the decisions we make in our own timeline? These are profound questions that push the boundaries of our understanding of reality. The many worlds interpretation offers a fascinating perspective on time travel, one that avoids paradoxes but opens the door to an infinite multiverse. It challenges us to rethink not only the mechanics of time travel but also the very nature of existence itself. As we continue our journey through these theories, we'll next explore the Alcubierre drive, a concept that could make faster-than-light travel, and by extension, time travel, a reality. Stay with us as we dive into the science behind bending spacetime itself. Now, let's venture into a theory that feels like it's straight out of science fiction: the Alcubierre drive. This concept, proposed by physicist Miguel Alcubierre in the 1990s, offers a tantalizing possibility: bending spacetime itself to achieve faster-than-light travel, and by extension, time travel. Unlike traditional methods that rely on moving through space, the Alcubierre drive works by manipulating the fabric of spacetime around a spacecraft. Here's how it works. Imagine spacetime as a stretchy sheet. the Alcubierre drive would contract spacetime in front of the spacecraft, pulling the destination closer, while expanding spacetime behind it, pushing the starting point farther away. The spacecraft itself would remain in a stable bubble of flat spacetime, effectively riding this warp wave without actually moving through space in the conventional sense. This means the spacecraft could, in theory, travel faster than light without breaking the laws of physics, because it's not the spacecraft moving, it's spacetime itself that's being manipulated. One of the most exciting aspects of this theory is how it sidesteps the problem of time dilation, a major hurdle in traditional faster-than-light travel. According to Einstein's theory of relativity, as an object approaches the speed of light, time slows down for it relative to the outside world. But with the Alcubierre drive, since the spacecraft isn't moving through space, time dilation wouldn't apply in the same way. This opens up the possibility of traveling vast distances in a short amount of time, effectively allowing for time travel into the future. However, there's a catch. The Alcubierre drive requires something called exotic matter, a theoretical substance with negative energy density, to create the necessary warp bubble. Exotic matter has never been observed in nature, and its existence remains purely hypothetical. Even if it does exist, the amount required to power an Alcubierre drive would be staggering, far beyond anything we could currently produce. Another challenge is the potential for catastrophic effects. Some scientists have speculated that the energy required to create a warp bubble could release massive amounts of radiation, posing a serious risk to anything in its path. There's also the question of how to control such a drive once it's activated. Stopping or steering a warp bubble could prove to be an insurmountable engineering challenge. Despite these hurdles, the Alcubierre drive remains a fascinating concept that pushes the boundaries of our understanding of physics. It challenges us to think beyond conventional methods of space travel and consider the possibilities of manipulating spacetime itself. As we continue to explore the mysteries of the universe, theories like this remind us that the line between science and science fiction is often thinner than we think. Next, we'll delve into another intriguing idea: time travel through consciousness. Could our minds hold the key to traversing time? Stay with us as we explore this mind-bending possibility. Now, let's shift our focus from the physical manipulation of spacetime to something far more intangible: the human mind. Could time travel be possible not through machines or exotic matter, but through the power of consciousness itself? This idea, often explored in philosophy and speculative science, suggests that our minds might hold the key to traversing time in ways that defy conventional understanding. At the heart of this theory is the concept of mental time travel, the ability to project our awareness backward or forward in time, reliving past experiences or envisioning future events. While this might sound like something out of a science fiction novel, there's a growing body of research in neuroscience and psychology that explores how our brains process time and memory. Studies have shown that our perception of time is highly subjective and can be influenced by factors like attention, emotion, and even altered states of consciousness. One intriguing possibility is that advanced meditation techniques or deep states of focus could allow individuals to access different points in time mentally. For example, some practitioners of mindfulness and transcendental meditation report experiencing moments where time seems to dissolve, and they feel a profound connection to past or future events. While these experiences are often described as spiritual or mystical, some scientists speculate that they could be glimpses into the brain's ability to manipulate its own perception of time. Another angle to consider is the role of dreams. During REM sleep, our brains create vivid, often nonsensical scenarios that feel real in the moment. Some researchers have proposed that dreams could be a form of mental time travel, allowing us to explore alternate timelines or hypothetical futures. While this remains speculative, it raises fascinating questions about the nature of time and consciousness, Of course, the idea of time travel through consciousness comes with its own set of challenges. For one, it's difficult to measure or prove subjective experiences like altered states of awareness. Unlike physical theories of time travel, which rely on observable phenomena and mathematical models, mental time travel is deeply personal and varies from individual to individual. Additionally, even if such experiences are real, it's unclear whether they could be controlled or harnessed in any practical way. Despite these uncertainties, the concept of mental time travel invites us to reconsider the boundaries of human potential. It suggests that time, as we understand it, might not be as fixed or linear as we think. By exploring the mysteries of consciousness, we might uncover new ways to interact with time itself, not through machines or exotic physics, but through the power of our own mind. As we continue to explore the possibilities of time travel, let's turn our attention to another fascinating paradox, the bootstrap paradox. How can something exist without a clear origin? Stay with us as we unravel this mind-bending concept. Now, let's venture into one of the most perplexing paradoxes in the realm of time travel, the bootstrap paradox. Imagine a scenario where an object or piece of information is sent back in time, only to become its own origin. Sounds like a mind-bending loop, doesn't it? That's exactly what the bootstrap paradox is all about. It's a concept that challenges our understanding of cause and effect, leaving us to wonder, can something exist without ever having been created? To break it down, let's consider a simple example. Suppose a time traveler goes back in time and gives Beethoven a symphony that he hasn't yet composed. Beethoven then publishes the symphony and it becomes a masterpiece. But here's the twist: where did the symphony originally come from? It wasn't created by Beethoven in this timeline, and the time traveler didn't compose it either. The symphony seems to have no true origin. It's as if it just appeared out of nowhere, caught in an endless loop of its own existence. This paradox doesn't just apply to objects or creative works, it can also involve information. Imagine a scientist who travels back in time and teaches Einstein the theory of relativity before Einstein develops it himself. In this case, who actually came up with the theory? The information appears to have no clear starting point, creating a loop where the knowledge is passed back and forth through time without a definitive origin. The implications of the bootstrap paradox are profound, especially when it comes to causality and logic. Causality, the principle that every effect has a cause, is a cornerstone of how we understand the universe. But the bootstrap paradox throws a wrench into this idea, suggesting that some things might exist without a clear cause. This raises questions about the nature of reality itself. Could the universe allow for events or objects that have no beginning? And if so, what does that mean for our understanding of time and existence? Some theorists argue that the bootstrap paradox isn't necessarily a problem, but rather a feature of time travel. In this view, the paradox represents a self-consistent loop where events are predetermined and cannot be changed. Everything that happens within the loop is part of a closed system with no need for an external cause. This idea aligns with the Novikov self-consistency principle, which we discussed earlier, suggesting that the universe naturally prevents paradoxes by ensuring that all events remain consistent. However, others see the bootstrap paradox as a glaring flaw in the logic of time travel. If objects or information can exist without an origin, it undermines our fundamental understanding of how the universe operates. It also raises practical questions. How would such loops be created in the first place? And what would happen if someone tried to disrupt the loop? As we grapple with these questions, the bootstrap paradox serves as a fascinating reminder of how time travel challenges our most basic assumptions about reality. It invites us to think beyond linear cause and effect, exploring the possibility that time might be far more complex and interconnected than we ever imagined. With this paradox fresh in our minds, let's turn our attention to another classic time travel conundrum, the grandfather paradox. What happens when a time traveler's actions threaten their own existence? Stay tuned as we dive into this iconic thought experiment. Now, shifting our focus to another cornerstone of time travel debates, we arrive at the grandfather paradox. This thought experiment is as iconic as it is unsettling, posing a question that strikes at the very heart of causality and existence. What happens if a time traveler goes back in time and prevents their own grandfather from meeting their grandmother? If successful, the time traveler would never be born, which raises the question, how could they have traveled back in time in the first place? At its core, the grandfather paradox challenges the idea of free will and the linear nature of cause and effect. It forces us to confront the possibility that altering the past could have catastrophic consequences for the future or even erase it entirely. But how do scientists and theorists grapple with this seemingly unsolvable problem? Let's explore some of the most compelling attempts to resolve this paradox. One approach comes from the Novikov self-consistency principle, which we touched on earlier. This theory suggests that the universe has a built-in mechanism to prevent paradoxes. In the case of the grandfather paradox, any attempt to alter the past would be thwarted by the laws of physics. For example, the time traveler might find it impossible to actually harm their grandfather, or their actions might inadvertently lead to the very events they were trying to prevent. In this view, the timeline remains consistent and the paradox is avoided. Another intriguing solution comes from the many worlds interpretation of quantum mechanics. According to this theory, every decision or action creates a branching timeline. If a time traveler were to go back and prevent their grandfather's meeting with their grandmother, they wouldn't erase their own existence in the original timeline. Instead, they would create a new, parallel universe where they were never born. In this way, the paradox is resolved by the existence of multiple realities, each with its own version of events. Some theorists take a more philosophical approach, arguing that the grandfather paradox highlights the limitations of human imagination when it comes to understanding time. They suggest that time travel, if it were possible, might operate under rules that are entirely different from our everyday experience of cause and effect. In this view, the paradox isn't a flaw in the logic of time travel, but rather a reflection of our incomplete understanding of how time truly works. The grandfather paradox also raises ethical questions about the consequences of altering the past. If time travel were possible, would it be morally justifiable to change historical events, even if it meant risking one's own existence? These questions don't have easy answers, but they remind us that time travel isn't just a scientific curiosity. It's a concept that forces us to confront profound questions about identity, responsibility, and the nature of reality itself. As we ponder these possibilities, the grandfather paradox serves as a powerful reminder of how time travel challenges our most fundamental assumptions. It invites us to think beyond the linear flow of time, exploring the idea that the past, present, and future might be far more interconnected than we realize. With this paradox fresh in our minds, let's turn our attention to another fascinating concept: time travel through quantum entanglement. How could the strange behavior of particles at the quantum level open the door to traveling through time? Stay tuned as we explore this cutting-edge theory. Now, let's venture into the strange and fascinating world of quantum entanglement and its potential connection to time travel. Quantum entanglement is one of the most mind-bending phenomena in physics, where two particles become linked in such a way that the state of one instantly influences the state of the other, no matter how far apart they are. This instantaneous connection seems to defy our everyday understanding of space and time, leading some scientists to wonder, could entanglement hold the key to traveling through time? At the heart of this idea is the concept that entangled particles might allow for communication across time itself. Imagine two particles entangled in such a way that one exists in the present and the other in the future. If we could manipulate the particle in the present, would it affect its entangled partner in the future? Some theorists suggest that this could create a kind of bridge through time, enabling information or even matter to traverse temporal boundaries. However, the challenges of harnessing quantum entanglement for time travel are immense. For one, entanglement is incredibly fragile. Any interaction with the environment can break the link between particles, making it difficult to maintain the connection needed for time travel. Additionally, while entanglement allows for instantaneous correlation between particles, it doesn't provide a clear mechanism for sending meaningful information or objects through time. The process would require a level of control over quantum systems that is far beyond our current capabilities. Another major hurdle is the potential for paradoxes. If entanglement could be used to send information back in time, it might create scenarios similar to the grandfather paradox, where actions in the past could alter the future in unpredictable ways. This raises questions about causality and whether the universe would allow such disruptions to the timeline. Some theories suggest that the laws of physics might inherently prevent these paradoxes, but the details remain speculative. Despite these challenges, the implications of quantum entanglement for time travel are profound. If scientists could unlock the secrets of entanglement, it might not only revolutionize our understanding of time, but also open up entirely new possibilities for communication and exploration. Imagine a future where we could send messages to the past or receive signals from the future, fundamentally changing how we perceive and interact with time. As we explore this cutting-edge theory, it's clear that quantum entanglement offers a tantalizing glimpse into the potential for time travel. While the practical applications remain uncertain, the idea that particles could be connected across time challenges our understanding of reality and invites us to rethink the very nature of existence. With this intriguing possibility in mind, let's shift our focus to another groundbreaking concept, the holographic principle. Could the universe itself be a hologram, and if so, how might this allow us to manipulate time? Stay tuned as we dive into this next theory. Now, let's step into a theory that feels like it's straight out of science fiction but is grounded in cutting-edge physics, the holographic principle. This mind-bending idea suggests that our entire universe might be a hologram, a projection of information encoded on a two-dimensional surface. If this is true, it could completely reshape our understanding of reality and potentially open the door to time travel. The holographic principle stems from the study of black holes and the strange behavior of information at their event horizons. Scientists discovered that all the information about matter falling into a black hole isn't lost but is instead encoded on its surface. This led to the radical idea that the universe itself might work in a similar way, that everything we see, from galaxies to stars to ourselves, could be a three-dimensional projection of information stored on a two-dimensional boundary. Think of it like a movie projected onto a screen, where the screen holds all the data needed to create the illusion of depth and movement. So, how does this connect to time travel? If the universe is a hologram, then time itself might be part of this projection. Manipulating the underlying information could, in theory, allow us to alter the flow of time. Imagine being able to rewrite the code of reality, adjusting the past or future by changing the information on the cosmic screen. This could provide a way to travel through time without the need for wormholes or black holes, simply by reprogramming the holographic data that constructs our universe. Of course, the challenges are enormous. For one, we don't yet fully understand how the holographic principle works or how to access and manipulate the information it describes. The scale of such an endeavor is almost unimaginable, requiring technology and knowledge far beyond our current capabilities. Additionally, the implications of altering the universe's code are profound. Would changing the past create alternate timelines, or would it simply overwrite reality as we know it? These are questions that push the boundaries of both science and philosophy. Despite these hurdles, the holographic principle offers a fascinating perspective on time travel. It suggests that time might not be a fixed, linear progression, but a dynamic, malleable construct shaped by information. If we could ever harness this principle, it could revolutionize not just our understanding of time, but our ability to interact with it. As we ponder this extraordinary idea, let's turn our attention to another captivating theory: time travel in fiction versus reality. How do the imaginative portrayals of time travel in movies and books compare to the real scientific theories we've explored? Stay with us as we dive into this intriguing comparison. Now let's shift gears and explore a fascinating intersection of science and storytelling: time travel in fiction versus reality. From blockbuster movies to best-selling novels, time travel has been a staple of imaginative storytelling for decades. But how do these creative portrayals stack up against the real scientific theories we've been discussing? And how has fiction shaped the way we think about time travel? In fiction, time travel often takes on a dramatic and visually stunning form. Think of iconic films like Back to the Future, where a DeLorean becomes a time machine, or Interstellar, where black holes and wormholes play a central role in bending time. These stories captivate us with their bold ideas and thrilling adventures, but they often take creative liberties with the science. For example, the idea of hopping into a machine and instantly traveling to a specific point in time is far simpler than the complex realities proposed by theories like relativity or quantum mechanics. Books, too, have played a huge role in shaping our perception of time travel. H.G. Wells' The Time Machine introduced the concept of a device that could move through time, while novels like The Time Traveler's Wife explore the emotional and personal consequences of time travel. These stories often focus on the human experience, weaving time travel into themes of love, loss, and destiny. While they may not always adhere to scientific accuracy, they succeed in making time travel relatable and emotionally resonant. But how does fiction influence our understanding of real-world science? For many people, their first exposure to time travel comes from movies or books, not scientific papers. This means that fictional portrayals often set the stage for how we imagine time travel works. For instance, the idea of a time loop, popularized by films like Groundhog Day, has become a cultural shorthand for repeating events, even though it's not a direct reflection of any scientific theory. Similarly, the concept of alternate timelines, seen in stories like Doctor Who, has sparked widespread fascination, even as scientists debate whether such phenomena could exist. That said, fiction doesn't just simplify science, it can also inspire it. Many scientists and researchers have cited science fiction as a source of inspiration for their work. The imaginative possibilities presented in stories often push the boundaries of what we think is possible, encouraging us to explore new ideas and challenge existing theories. In this way, fiction and science have a symbiotic relationship, each influencing and enriching the other. So, while the time travel we see in movies and books may not always align with the complexities of real-world physics, it plays a crucial role in sparking curiosity and imagination. It invites us to dream big and ask questions, bridging the gap between what we know and what we can imagine. And as we continue to explore the mysteries of time, both in fiction and reality, one thing is clear: our fascination with time travel is as timeless as the concept itself. With that in mind, let's turn our attention to the final piece of the puzzle: the role of dark matter and dark energy in time travel. Could these mysterious forces hold the key to unlocking the secrets of time? Stay with us as we delve into this intriguing possibility. Now, let's venture into the shadowy realms of the cosmos, where dark matter and dark energy reign supreme. These enigmatic forces make up the vast majority of the universe, yet they remain some of the most elusive and poorly understood phenomena in science. Could they hold the key to unlocking the secrets of time travel? Let's explore this intriguing possibility. dark matter, though invisible and undetectable through conventional means, exerts a powerful gravitational pull that shapes the structure of galaxies and the universe itself. Scientists estimate that dark matter makes up about 27% of the universe's total mass and energy. But what does this have to do with time travel? Some theories suggest that dark matter could create gravitational anomalies capable of warping spacetime in ways that might allow for time manipulation. Imagine a region of space where dark matter is densely concentrated, bending time itself like a cosmic trampoline. While this remains speculative, the idea opens up fascinating avenues for exploration. Then there's dark energy, an even more mysterious force driving the accelerated expansion of the universe. Unlike dark matter, dark energy doesn't clump together. It permeates space uniformly, acting as a kind of anti-gravity. This expansion raises questions about the nature of time itself. If the universe is stretching faster and faster, could dark energy influence the flow of time on a cosmic scale? Some researchers speculate that manipulating dark energy might allow us to control the rate at which time passes, potentially creating pathways for time travel. The challenge, of course, lies in the fact that we still know so little about these forces. Dark matter and dark energy don't interact with light or ordinary matter in ways we can easily detect, making them incredibly difficult to study. Yet, their sheer dominance in the universe suggests they play a fundamental role in shaping reality as we know it. If we could harness their power, the implications for time travel could be revolutionary. One intriguing idea is that dark matter and dark energy might work together to create stable wormholes or other spacetime shortcuts. These could serve as bridges between different points in time, allowing for travel without violating the laws of physics. While this remains firmly in the realm of theory, it's a tantalizing possibility that underscores the importance of continuing to study these mysterious forces. As we wrap up our exploration of the 20 theories that could explain time travel, it's clear that the universe is far more complex and wondrous than we often imagine. From the bending of spacetime to the mysteries of dark matter and dark energy, each theory offers a unique lens through which to view the possibilities of time travel. While many of these ideas remain speculative, they remind us of the boundless potential of human curiosity and imagination. So, what's your favorite theory? Let us know in the comments below, and don't forget to like, subscribe, and hit the notification bell for more deep dives into the mysteries of the cosmos. Until next time, keep exploring. As we bring our journey through the 20 theories of time travel to a close, it's remarkable to reflect on the sheer diversity of ideas that science and imagination have brought to the table. From Einstein's groundbreaking theory of relativity to the mind-bending possibilities of wormholes, closed time-like curves, and even the enigmatic role of dark matter and dark energy, each theory offers a unique perspective on how we might one day traverse the fabric of time. These ideas remind us that the universe is far more complex and mysterious than we often realize, and that the pursuit of understanding it is a never-ending adventure. What's fascinating is how these theories span the spectrum from the deeply scientific to the wildly speculative. Some, like the Alcubierre drive or quantum entanglement, are rooted in cutting-edge physics, while others, such as time travel through consciousness or the holographic principle, push the boundaries of what we consider possible. Yet, all of them share a common thread. They challenge us to think beyond the limits of our current knowledge and imagine a future where the impossible might just become reality. Of course, many of these theories remain in the realm of speculation, and the road to proving or disproving them is filled with challenges. But that's the beauty of science. It's a journey of discovery where every question leads to new possibilities. Whether it's the paradoxes of closed time-like curves or the tantalizing potential of time crystals, each theory invites us to explore, question, and dream. So, what's your take on all of this? Which of these 20 theories resonates with you the most? Is it the elegance of Einstein's space-time, the intrigue of wormholes, or the mystery of dark matter and dark energy? Let us know in the comments below. We'd love to hear your thoughts and spark a conversation about the endless possibilities of time travel. If you enjoyed this deep dive into the science and speculation of time travel, don't forget to hit the like button, subscribe to the channel, and ring that notification bell so you never miss out on our explorations into the mysteries of the cosmos. Until next time, keep questioning, keep imagining, and keep exploring the wonders of the universe. Who knows, the secrets of time travel might be closer than we think.